ones that can escape the room. And so I just decided to give you an overview, and rather than just cram it full of mathematics. You can see what those four coupled equations are in the last thing, between the probabilities of the people, the probabilities of the answers being correct, the values of the people as how well they can converge on the values that are given by the median people, and the values of those median people given for each question. And one thing I wanted to mention, there are a lot of questions that are very, very hard, that are worthless. For example, there's a rock on the ground. I say, what's the mass of that rock? And you want to know all these 55 binary digits. That's totally useless. Nobody cares. The mass of the protons are of great importance, and that's what I mean by valuing the question. You want people to say, that's a ridiculous question. So you want probably 4 or 5 people just judging between 0 and 100 to get some range for what another person has come up with the question as a check. Okay, this is
Joe, excuse me.
Yeah.
May I ask
Yeah.
one more question? Related to proton mass. If you give this example, I think we cannot believe in prediction of proton mass. It doesn't matter what is output will be. We must measure this, and
Right.
that's it.
So the people that are going to overlap would be 2 teams. It'd be Carl's team and a team out of Berkeley, and they'd both be out there running experiments on some large accelerator, and they'd be compiling their data. And all of a sudden, the NSF wants to know what the next 3 binary digits are. So they look at their preliminary data and they make intelligent guesses, even though they haven't published it yet. In other words, you're not going to just guess out of the blue. I mean, nobody's going to do that. That's a known thing. Now, for whether you're going to win a war or what the Dow Jones is going to be, Dow Jones, you may do a lot of research.
I mean, it should be defined, well-defined in domain where it's applicable. For example, again,
Yes.
for physics, if you 20 years ago will ask what is neutrino mass, all experts probably will get answers.
And the Earth is flat.
It has no any meaning.
And I didn't have time to cover that. But it turns out that in the coupled nonlinear equations, you can also have attractors that go the wrong way. And all you have to do is start asking questions about religion, questions about whether the Earth is flat at the wrong century, and all kinds of things like that. And you got agreement. And you even had people at the end of the last century who said, basically all that's known about physics is known. We just have some details to do. And so people did not understand, we often don't understand what we don't understand. And that's going to happen. So there's certain domains where this is going to be, and certainly for the mass of the proton, you've got to have experts. You're not going to guess out of intuition. You're not going to sit there and think, I think this one's going to be a 1. Like guessing the next digit in pi. Okay, so let me go to this. The problem I want to address here is the retention of information when we have a system that we know is chaotic, and we've got entropy increasing all the time. Entropy is ever present in the world, and we're all familiar with the second law of thermodynamics. Yet somehow another order seems to persist, and that this is a question that always comes up in these philosophical talks. How do we get life in the midst of this? And I'm not going to talk philosophically here. I'm going to talk very mathematically, and I'm going to address this problem and see, is there some tiny way that we can imagine in simple systems where entropy is present that order could persist for a period of time? And we'll find out that it can, and I'll show you how. The very simple system I want to choose is the simplest of possible systems. It only has 2 components. For those of you who have seen my previous talk, we'll be looking at the general linear group in 2 dimensions and the transformations that are there, the Lie group associated with that. A physical model for the system we're going to be talking about is very simple, though. It's an aquarium filled with water. So I want you to imagine we have this tank of water up here, and we put a partition directly down the middle, and that partition has a hole in it, and it's divided into 2 parts, and that hole allows the water to pass from each side to the other side, in other words, to diffuse. On one side, the water is pure, and on the other side, at time t is equal to 0, we put a whole bunch of red bacteria. There's a reason for that. I didn't want just red dirt over there. I wanted something that could die or could multiply for the time being, because the model will make more sense if I describe it that way. And what's going to happen is these red bacteria, I won't let them get born, have sex or whatever they do. Bacteria can't get greater or lesser for the time being, but they can only migrate back and forth, and they do this with equal rates into the two halves. Okay? I just said that to wake you up. We will study the process of diffusion as a continuous Markov transformation where the bacteria can migrate through the hull. We'll measure that information by the ratio of bacteria on one side, the ratio on the other side, equivalent to Shannon or Rene entropy. Let me mention something about that. If the amount of bacteria is diffusing, we could say that when we started out, if the red is over here, we call that a 1. If the red is over here, we call it a 0. And as the bacteria migrate, at a certain point you're looking at the tank and you say, I don't know whether this is more red or that's more red. At that point you've lost the information. It's not discernible at some point what your starting point was, and there's no irreversibility. You can't reverse this transformation. So what we want to know is, can we stop it so that at a certain ratio of redness to unredness, or a number of bacteria here to number of bacteria here, we'd say the information's frozen. More formally, what we would do is we'd take the number here and add it to the number there and then normalize that to give a probability. So you'd have a P on the left and a P on the right that's summed to 1. And then we could compute the Shannon entropy in terms of those two probabilities, or we could take the log base 2 of the sums of the two squares and get a second order Rane or another entropy function. Now in 2 dimensions, it doesn't matter which you measure. If the ratio of the two sides is the same number of red bacteria, you get the same amount of, you get constancy for Shannon, you get constancy for Rane of any order. That's not true for higher orders, but it is true for order 2, so we don't have to even worry about what type of entropy. We don't have to put the formulas up, we can just look at the results. I want to talk about diffusion, and the diffusion, the infinitesimal diffusions, I'm going to rob Peter to pay Paul, which we'll see here. These are the infinitesimal generators to take a fraction of something and give it to someone else. When we exponentiate these two transformations, it'd be like, I gave to Robert 1% of the money I had with me. And the other transformation is Robert gives me 1%, or let him give me 2% of how much he has with him, if we wanted to do it unequivocally. When we exponentiate those, you see this transformation here, which is a transformation that gradually takes away from Peter and pays Paul, takes away from Paul and pays Peter. And you can see that, I mean, it's very quick. You just take that and expand that in an exponential, and you can see what that group is. And this is a very interesting Lie group. It's a Markov type Lie group. It's not semi-simple. It's not abelian. It has two parameters. The commutator of A and B is equal to A minus B, or you can rewrite it and it's A alone. And so it's isomorphic to most of those groups you think of that have only two elements. The transformation gradually transforms a fraction of x2 into x1, and it preserves x1 plus x2. That's what a Markov transformation does. So we're not losing or gaining any bacteria at this point. You note that for the columns, the sums was unity. You note for the Markov process, if I add these, I get 1, I add these, I get 1, and that's what we have to have for a Markov process.
So there's a plus. There's a plus.
Huh?
There must be one of them. There's a minus and a plus.
Oh, I forgot the minus signs here. Yeah, put in minus S for S in those places. I was tired when I typed this. In fact, I only added that slide about an hour ago.
The sum is 1, yes.
Yeah.
But this one second.
Okay, the transformation gradually transforms a fraction of x2. I did that one. And if I let both of these processes run simultaneously, it's straightforward to see where you just sit down and you take that matrix that would be the sum of the two, put time in there, and you find this. So you can see at time t is equal to 0. At t is equal to 0, this becomes 1. 1 minus 1 is 0. And so I retrieve the identity matrix. There, time t is equal to 0. And at time t is equal to infinity, I get 1, 1, 1, 1. Or 1 half, 1 half, 1 half. So I get the equal mixtures of the two at time t is equal to infinity, and I can't go back. So I've got, that would be the Markov process. It's basically a rob Peter to pay Paul. Equivalently, we could have Peter with $1,000 and Paul with 0. Every instant of time, you give a fraction to each other. Eventually, you can't discern who had the most money. That's the whole point with diffusion. The point I'm trying to make is you lose information with diffusion, in the formal sense of information. But in the general linear group, there are two other transformations that we haven't looked at. And those two are, I'll give an example, I'm sorry. Two transformations that scale the axes proportionally, like exponential birth or death of the bacteria. While the diffusion conserves the bacteria, the scaling transformations allow for both growth and death. This is identical to populations in two states that can migrate. So you could imagine first of all, we have only in the world North and South Carolina. And the people can move from North Carolina to South Carolina or South Carolina to North Carolina, so they migrate back and forth. In North Carolina, you can have one death or birth rate, and in South Carolina, a different one. And so eventually you get to some stable population if you had only diffusion, but not if you have birth that's going to grow exponentially. And that's what the two scaling transformations do. So everything we're doing is linear here. Here are the two scaling transformations. And now I can put all these together. I don't know if you can, how well you can see this. And you can expand this and find that this is the solution to the expansion of this by taking out all the terms. And basically what I've done is this rho right here, it's rho, rho. The rho is a measure of the diffusion rate. The eta plus eta minus eta is the asymmetry between diffusing to the right and diffusing to the left. The alpha is the asymmetry in growth, and the gamma is an overall symmetry in growth. So gamma and alpha are the two scaling transformations for overall growth of the whole system, or growth of this relative to a decay of that. So believe it or not, you have 4 parameters there, and those are complete for the general linear group, or all transformations in 2 dimensions. And you get this thing here, which are hyperbolic functions.
Why is beta, Joe?
Define beta
Okay.
in terms of alpha squared, which is the asymmetry in the growth, and eta, which is the asymmetry in the equilibrium. And I'm going to set eta equal to 0 because it doesn't add anything. We want a completely symmetric situation. So we can think of this G of t as giving us a time evolution on some original numbers here that start out at like 1 and 0. And you can very simply show that that time development being in 2 dimensions is equivalent to a second order differential equation. But this would be the differential equation that's equivalent to that. And you can solve the differential equation and get this form here. And it's possible to adjust the uneven growth so that the diffusion is arrested, and this can be done over a continuous range. What I'm basically saying there is I can have birth and death rates and adjust those so that for the continuous diffusion that I have, I can adjust those so that I freeze the ratio of what I have on one side to what I have on the other. No big deal, you knew that before you came here. But what we're going to ask is it possible with no overall growth to have discrete integer solutions? Well, the discrete integer solutions, let me back up just a minute and tell you what I mean by this. What I mean is I want to consider the simplest possible situation with no overall growth. And with no overall growth, it means that basically we want to have uneven growth, and we want to see if this uneven growth can compensate for the pairwise diffusion. Now, I looked at that for a long time before I thought of the idea of quantization. The quantization idea comes from the following. If you take a tree just doesn't put out a huge leaf. It puts out a stem, then it puts out another limb. Then that limb puts out one leaf, then this one puts out one leaf. It's all a discrete process. It is a quantization on a classical level. I don't know if you understand what I'm saying or not, but most living things do things in quantized stages. They don't just become larger and larger and larger in order to fight entropy, which would be the other solution. So what I did was I chose the simplest situation that you can have. Since I'm starting my group, this general linear group, at time t is equal to 0, it has determinant 1. I require that it stays with determinant 1 forever. So I then say, with determinant 1, what are the simplest situations that have both diffusion and allow uneven growth? And the simplest one that you can have is a diffusion off the diagonal, which would be 1. If the matrix is going to have a determinant of 1, which it had since the beginnings because it started at the identity, It grows continuously, so it has a constant determinant of 1. A 2 and a 1 is the only one possible. Now the question is it possible to take these 4 integers and match those with the hyperbolic sines and cosines and exponentials in the previous transformation? And what you have to have for that is each one of those functions, which are different, except I've made the 2 off-diagonal ones the same by making the diffusion the same. So I have 3 conditions. They all have to hit an integer at the same time. Obviously, they all hit integers, but all 3 of them must hit these integers, these exact integers at the same time. So you can ask, is there a solution? And the answer is affirmative. And after you do that, the time development of the system in 1 unit of time gives you this again. Then in the second unit of time, it gives you the rest, and these are all the Fibonacci sequence. So the Fibonacci sequence is the simplest sequence that is generated by the 2-dimensional group allowing diffusion and uneven growth that has a unit determinant at the lowest level.
This is a solution to the difference, linear difference equation.
Yeah, it's all this same
with
thing.
this basic matrix, which you start with 2 and 1.
And the eigenvalues of that are, of course, the golden ratio. But one of the interesting things is you can then say, well, this is in one case. What about other cases where we could have a unit determinant, for example, here? In other words, if I take the off-diagonal element to a diffusion rate of 2, and I still require a unit determinant, then I have to go to a 5 and a 1. If I take this, then I can get a sequence like this. And it turns out that this sequence has 2n minus 1 plus n minus 2. You know the Fibonacci sequence is the sum of the last 2 to get it. Here we have twice the last one plus the 1 before. And then another sequence of these, which is 3 times the last one plus the 1 before, which turn out to be, once you go through this set of numbers with your general linear transformation, you'll go through it in every integer multiple of that amount of time.
The last column, basically. Yeah.
Huh?
The numbers, the entries there is the last column. What I'm saying is that you just, what matters is the last column, the second column.
Yes, yeah, that's true. And so you get a whole series, but now it gets more complex and interesting than that, because what you can do is say, let's not just look at quantized order that can be maintained for determinant of 1, but other types of determinants. And let's not restrict it to second order matrices, but let's look at 3 by 3, and then you're looking at the general linear group in 3 dimensions. You're looking to see if 3 systems could have entropy among them and have uneven growth so that they maintain imbalances that would be very important. And then, of course, very quickly you get to equations that you won't be able to solve, because in 2 dimensions you have quadratics, but when you get to 5 by 5, you're not going to solve anything generally. And so it's kind of interesting what you might achieve as you go up there. If you look at one of the transformations that I got out of this, you get something very interesting. It turns out that we get out of this an interpolating function that interpolates all of the functions, becomes a generating function for the Fibonacci sequence. And that's very interesting. You know the gamma function smoothly moves among the factorials. I'm not aware, although that it may be, I just haven't found it, of any function that people have found that smoothly interpolates Fibonacci numbers. But these functions that come out with this, I want you to look at the form that this has. And can y'all see it in the back?
It's not interpolating the Fibonacci, you just get the coefficients to be the Fibonacci.
Yeah, this is the exponential series with the Fibonacci coefficients in the front.
So it's not like f of t literally interpolates. When you interpolate it, you get the golden mean to the end plus the inverse of the golden
Yeah, and you don't know that you're going to get something this neat as an interpretation.
Interpolation here, what Shmuel says is that factorial is that the value of the function on integers, it gives you integer again, and the gamma of n plus 1 is what we call n factorial.
Yeah.
As a equality of values, and here as a generating function. So it's different. Yeah. So you discuss the generating.
Okay, so I would just summarize by saying the interpolating function and the associated differential equation for the Fibonacci sequence is one thing we got. A view of the sequence as information retention in the presence of entropy. Fibonacci-like sequences that are additional to that, each with their own generating functions and information retention values. If you're curious, you've heard of this golden mean, which everybody talks about like it's some mystic thing. I mean, you're going to go to India or China or somewhere and go to a mountain to learn what this thing means and what the true value of this thing is, or whatever. I mean, there are people that approach this thing with mysticism. And many people put it in the same level of importance as pi and e and 1 and so forth like that.
You know what? The
But,
first man who
what
discovered
we have here-
irrational numbers was drowned.
Yeah.
Was drowned. Pythagoreans basically killed him. They took him to the sea.
But let me tell you what the next one is.
That news guy. You know,
The next one is
so
one is something you already know, and the next quote golden ratio turns out to be in that next sequence 1 plus the square root of 2.
Oh, yeah.
And then the next one after that is more complex and then more complex. So it actually, with this trivial-like exercise, we could actually go out and make predictions, and we could say, do any living forms like they do with sunflowers and shells, which I didn't review all that. That's in the popular literature, and you've seen that. I have a book up here if anyone wants to see it. It's full of all these things. I tried to photograph it, and my camera didn't work right and stuff. Anyway.
This is supposed to be James Bernoulli, the great Bernoulli spiral.
And I finished on Yes.
But you know, so Fibonacci was already pretty late, so we can say that the implicit discovery of irrational numbers, which you have there, is only 2,000 years after Pythagoreans. You see, because square root of 2 was discovered by these guys in the 6th century, 5th century. But the golden mean, of course, comes, roughly speaking, 2,000 years later. 1500, Fibonacci.
No. The golden mean was discovered by Pythagoras when they
way
managed
back.
to actually
Used it for the
construct
Parthenon
the
and so
pentagon.
forth. But anyway, if I could just make just a couple of statements.
But
I think the game theory does involve rather well-defined sets of coupled nonlinear equations for which one can look at different types of iterative solutions. You could use computer models with simulations. You could look at proofs. Are there equilibria? When are the equilibria present? You could search for something equivalent to a Nash equilibrium. I'm not that good in my nonlinear equations, but I think those are interesting questions aside from just putting it on the web and playing with it, which I'm very interested in because I think it can actually be a tool that people can use to get information. Basically, it becomes an engine. And one person goes out and he gets money. He's the creator. And he makes the overall rules and sets the parameters. Then he turns the system loose. And then he deposits money in bank accounts and he gets information back. That's kind of an interesting game. And it is still a game. And people get rewards and they get payoffs and they compete against one another and they form alliances. It's in person, it's non-zero sum. Fibonacci is something that's non-trivial also, I think. You can go out and you can say, are these other ratios there? Do we find these sequences in any living things? And there's a whole set of them going to more and more complex systems. That is a pure conjecture, I want to say that this is nature's way of fighting entropy. However, that's only a simple two system. And just like the Library of Congress can be made up of coin flips, ones and zeros, it just takes an awful lot of coins to represent it. Likewise, you could represent your DNA or whatever by the equivalent, somehow or another, buried concept of information where these things grow exponentially, but something has to happen and they have to die. They have to pass the information on to a subsequent another piece because they can't grow exponentially. So in a certain sense, you could say it explains death and rebirth. So,
Any other comments or questions? Yes.
So I don't see why you say nature is fighting entropy.
Nature doesn't fight entropy, but ordered systems are fighting entropy, or they don't just order themselves automatically. I'm saying, how is information retained in something? I think you could design you could actually build a system like this that could have feedbacks that fed off of inequities, and it would maintain an order locally by exponentially growing unequally and retain the information there. That's what we do. We feed off of inequities in food and energy.
I might be misunderstanding your definition of alliances in your game theory,
Mhm.
but you said that it handled alliances well, but it seems that if fitness of answers is judged by deviation from the mean, if you have a sufficiently large alliance that's dedicated to misinformation basically, then wouldn't their answers influence the mean and thereby influence the fitness?
It would, but you don't want an alliance of a lot of people because you have to share the payoff. And so in fact, there becomes an optimization where you don't want to add any more people to your allowance because you've got to put the payoff and give them a fraction of that. So it's diminishing what you have. So your optimization problem is one of finding the smallest possible allowance that will give you a reasonably high payoff for the group. Do you see what I'm saying? Did I answer your question?
Basically.
Okay.
Question?
So the alternative Fibonacci-like sequences have never been seen in it.
I don't know. I'm not aware of there being seen. I don't know if anyone's ever looked for them. I mean, I'm not a biologist. I wouldn't know how to go out. I don't know a sunflower from a lily.
William, you have a question?
This systematic method of finding the most optimum team, is that actually being used in like when investment
they do.
companies put together a team who to fire and whom
The
to...
people in business and in computer science are aware of how you use various models for voting, and they do different things. Like they may, like Vladimir suggested, make corrections for the dependents among them, and you can get all kinds of very complicated models. This is just one model that I put up there. It really works pretty well in practice. It's very fast, and just running it on a PC, the crudest kind of PC, can handle hundreds and thousands of people, you know, with questions coming as fast as you can imagine. And each time it's recalculating every time a new question is asked, it goes back and computes every probability again, and every response is given in the past, and has to readjust the payoffs it's made, so it's overpaid people in the past. We'll have to subtract them in the future. So I didn't cover some of those things.
Well, let's thank the speaker again, and if you have more questions.
What we don't understand. And that's going to